So, hello everyone. In the last lecture, we are discussing the phase behavior of polymer solutions. So, specifically we looked at the conditions under which polymer solution can become unstable and phase separate into two different phases. We considered the Gibbs energy versus composition diagram, and on that diagram we marked the points which correspond to the stable, metastable and unstable regimes. Basically, the regions demarcated by the binodal points, they represent the regions of stability of homogeneous solutions. The region between the binodal and spinodal points, they represent the metastable region, where the thermodynamically the favorable state would be phase separated two phase state, but for that to happen there is a barrier that needs to be crossed, and then phase separation can take place through nucleation and growth. Further, we also identified unstable region, which is the region between the two spinodal points, and this region any tiny fluctuation can result in the phase separation of a homogeneous solution into two different phases. So, we also developed mathematical expressions starting from the Flory-Higgins equation for the spinodal curve as well as for the critical composition, the critical temperature and the critical Flory-Higgins interaction parameter. Further, we also briefly started discussing the thermodynamics of polymer blends. So, in this lecture we will continue that discussion on the thermodynamics of polymer blends, and we will also briefly talk about the thermodynamic and phase behavior of block copolymers. So, the content of this lecture is briefly summarized here. We will start with the Flory-Higgins equation for polymer blends, which we introduced in the previous lecture. Then we will use that Flory-Higgins equation to derive the expressions for spinodal curve as well as for critical point, which is the approach will be similar to what we discussed in the previous lecture for polymer solutions. We will also look at the case of asymmetric as well as symmetric blend, what these are and how the behaviors are a bit different. And finally, for polymer blends we will look at the phase diagram, a typical phase diagram for polymer blends, and we will see that it has features which are very similar to what we already observed for polymer solution phase diagrams. And towards the end of this lecture, we will briefly also discuss the phase behavior of block copolymers, and we will see that it shows some interesting features. So, as discussed in the last lecture, the Flory-Higgins equation for a polymer blend is very similar to the Flory-Higgins equation for a polymer solution. The only difference is the appearance of this term x1 here, and this x1 is nothing but the number of segments in the first polymer. So, as we have already discussed, polymer blends are a mixture of two different polymers, and x1 denotes the number of segments in polymer 1, x2 denotes the number of segments in polymer 2. So, the number of segments in polymer 1 x1, that is the extra term that appears here as compared to the equation for polymer solution. And the volume fractions of the first and the second polymer, the expressions for those also change a bit, because now both components are polymers. So, the number of segments of both the polymers will come into the volume fraction expression. So, we have phi 1 as x1n1 by x1n1 plus x2n2, and similarly phi 2 as x2n2 divided by x1n1 plus x2n2. If we take the delta Gm and divide that by the total number of lattice sites or the total number of segments present, which is x1n1 plus x2n2, what we can do is through this division reformulate the original Flory-Higgins equation for a polymer blend into a form where the right hand side only contains the volume fraction of the second polymer, which is phi 2. So, this again is something that we discussed towards the end of the last lecture. If you look at this expression, the expression here, the first two terms here, these two terms, these represent the contribution from the combinatorial entropy change of mixing, and we see that the difference from polymer solutions is here both these terms are actually contain either x1 or x2 in the denominator, so that both these terms are small in magnitude. What that means is that the entropy change of mixing is quite small for polymer blends, and it turns out that it is actually the interaction term, which is a term containing chi, this last term here, that is the term which dominates the thermodynamics of polymer blends. The entropy of mixing is small, and that contribution does not significantly play a role in deciding the thermodynamics of polymer blends. It is the interaction term which is the more important one. So, again if we start with this reformulated Flory-Higgins equation in where delta Gm is expressed in terms of phi 2 only, and if we as before, as discussed in the last lecture, if we again try to look at the condition for stability. So, the condition for stability we know is decided by the sign of the second derivative of this delta Gm with respect to phi 2. So, what we can do is differentiate this expression twice again, then see what expression we get, and how equating it to 0 can lead us to the expression for the spinodal curve. So, differentiating it once will give us the expression here, where these two terms here, these two terms come from the differentiation of this term here, and similarly these two terms come from the differentiation of this term here, and finally this term comes to us just by the multiplication of 1 minus phi 2 with phi 2. So, again we see that these can be cancelled, similarly the phi 2 here, that can also be cancelled. So, we end up with an expression which looks something like this, and now if we differentiate this expression one more time, because we are interested in the second derivative of the Gibbs free energy change, that is the term whose sign decides the stability of the polymer blend. So, the stability will be decided by the second derivative, and the second derivative is obtained by just differentiating this quantity one more time with respect to phi 2. So, if we do that, this term derivative of this with respect to phi 2 is 0, differentiation of this with respect to phi 2 will give us this term. Again if we differentiate 1 over x 2 with respect to phi 2, that is also 0, because x 1 and x 2 are constants as far as change with respect to phi 2 is concerned. Differentiating this will give this term, and finally differentiating this will just give minus 2 chi term. So, the second derivative of the Gibbs free energy chain with respect to the composition, which here is represented by phi 2. So, the expression for that second derivative is this, and as we have discussed before, if this quantity is less than 0, then we know that the blend will be unstable, and such a blend will not actually remain in a mixed state, it will phase separate into two different phases. Now, let us look at a condition where this second derivative is actually 0. So, the second derivative being 0, that is the condition for the spinodal point, as we have discussed in the previous lecture for polymer solutions. So, for polymer blends also the same condition will apply, and the second derivative, setting the second derivative to 0, that will provide us the location of the spinodal points. And so, if we use the expression for the del square delta Gm del phi 2 square that we derived in the previous slide, if we set that expression to 0, then from that by rearranging the terms, finally what we get is the chi, which is the Flory-Higgins polymer interaction parameter, because we are talking about blend now. So, here this chi s, where the subscript s denotes again spinodal. So, chi s is given by half of 1 over 1 minus phi 2 x 1 plus 1 over phi 2 x 2. So, this equation basically is the equation of the spinodal curve. So, if we plot chi s as a function of phi 2 using this equation, that will give us the spinodal curve as predicted by Flory-Higgins equation for a given polymer blend. Now, if we assume that chi depends on temperature using a functionality of this form, that is chi is equal to a plus b by t, then we can substitute that expression for chi s, which is a plus b by t, and again instead of t we are writing T s, because we are dealing with the condition for spinodal. So, that subscript s again denotes the temperature, denotes the spinodal condition. And if we rearrange the terms again, what we get is the expression for temperature, this temperature T s at the spinodal condition as a function of phi 2. So, from this equation as well we can plot the spinodal curve, where as phi 2 changes, how the temperature is changing, that behavior can be obtained from this equation, and then it can be plotted to get the spinodal curve. Next, again similar to what we did for polymer solution, for polymer blends also, if we want to determine the critical point, the condition for that is the derivative of this chi s with respect to phi 2 is 0. What that means is that if we plot chi s as a function of phi 2, then the critical point will correspond to the point where the curve will show a minimum. So, the spinodal, if we plot the spinodal curve, then the minimum of that curve corresponds to the critical point, and that is what we are trying to mathematically determine using this condition here. So, applying this condition, and we already have derived an expression for chi s in the previous slide. So, if we differentiate that expression with respect to phi 2, we get this expression here, and for the critical composition or the critical point, the condition is that this expression, that is this derivative, should be equal to 0. So, setting it equal to 0 and again rearranging the terms, what we get is phi 2 square over 1 minus phi 2 the whole square is equal to x 1 by x 2, and again in the next step we can just take the square root on both sides, and then finally rearrange the terms one more time, take this term up here and this term up here. So, we get this expression, and from this finally the expression for phi 2 at the critical point. So, this phi 2 c, which is the critical composition or the value of phi 2 at critical point, so that is what we obtain, and the expression for this critical composition is 1 over 1 plus x 2 by x 1 raised to the power half. So, next now that we have an expression for this critical composition, we can use this expression to obtain expressions for critical temperature as well as the critical value of the Flory-Higgins interaction parameter. So, earlier we have already derived that the temperature corresponding to the spinodal condition is this, and the expression is given on the right hand side here. And since we already know that at the critical point the composition is given by an expression like this, we can substitute this phi 2 here at both the points where phi 2 appears on in this expression. We substitute the expression for phi 2 c at both those points, then upon substitution we will get an expression for the temperature, and that temperature basically is the critical temperature. So, that is the temperature at the critical point, and again upon simplifying, so some simple rearrangement of the terms and then further taking some factor outside the brackets, that is this factor is common to both the terms here. Finally, the expression for T c or the critical temperature we will get as something like this. So, we see that this expression also contains a number of segments of both the polymers present in the blend as well as the parameters A and B, which relate the Flory-Higgins interaction parameter to the temperature. Next, now that we have an expression for critical temperature, we can also obtain an expression for the critical value of chi. So, we already have have derived an expression for chi s, which corresponds to chi at the spinodal points, and we know that the expression for the critical composition, that is the composition at which this curve shows a minimum, that expression is already derived to be this. So, again if we substitute this expression for phi to c at both these points here, then upon that substitution, the chi that we get, that chi is the critical Floor-Huygens interaction parameter, which is the value of chi at the critical composition. So, again upon substitution and rearrangement, the expression that we end up with is something like this. So, this is the critical chi expression for that. For the and we can further simplify it by dividing both the terms in the numerator by x2, and the final expression that we get for critical chi is half multiplied by 1 over square root of x2 plus 1 over square root of x1 whole raised to the power 2. So, this expression again is the expression for the critical Floor-Huygens interaction parameter. The expression for critical temperature we have already derived to be this in the previous slide. So, now these expressions apply to any blend which can be described by the Floor-Huygens equation. Now, if we consider a special case where the blend that we have is symmetric, okay. So, we say that the blend is symmetric when both the polymers have the same number of segments. So, both the polymers constituting the blend have equal number of segments. So, what that means is that x1 and x2 will be equal for a symmetric blend, and let us say that we represent the x1 and x2 both as by this common symbol x. So, now let us see what happens to the expression for the critical composition, the critical chi as well as the critical temperature for the special case of a symmetric blend. So, if we substitute x2 equal to x1 here, this second term just becomes 1. So, for critical composition the value that we get is just half. So, for a symmetric blend the critical point always will correspond to a composition of 0.5, and what that implies is that minimum in that curve, the minimum of the spinodal curve will correspond to a composition of phi 2 equal to 0.5. Next, if we consider the critical temperature Tc, so again in this expression if we set x2 equal to x1, so this term becomes 1. So, we get 1 plus 1 2, and this is squared here. So, 2 square will get 4 in the numerator here, and we have a 2 here in the denominator. So, we will end up with a 2 by x2 term. So, this x2 we are, since x1 and x2 are equal, we are representing both as x. So, this term will simply become 2 by x. So, the critical temperature, that expression reduces to b over 2 by x minus a. And finally, the critical chi parameter. So, again in the expression that we had here, if we substitute x1 and x2 to be equal and replace them by just x and take that out as common, then in here inside the bracket we will be left with 1 plus 1, which is 2, and its squared. So, we will get 4 again, and we have a factor of 2 dividing it here. So, we will end up with a factor of 2 in the numerator, and this square root of x, when it is taken out, since there is a square present here, that will become just x in the denominator. So, this xc simply reduces to 2 by x for the case of a symmetric blend. Now, the larger the value of x, the smaller will be the value of this critical chi parameter. And if we just rearrange the terms here, then this product of x time chi c, so this x time chi c, where chi c is a critical Floor-Huygens parameter, that product is equal to 2. So, what this tells us is that this product x times chi c at the critical point, the value of this product is 2 for a symmetric polymer blend. Now, that we have discussed the equation for spinodal curve as well as the expressions for critical point, now let us again try to look at the phase behavior as well as the delta G diagrams of this polymer blend graphically, as we did in the case of polymer solution, so that we get better understanding of this topic. So, let us consider an asymmetric blend first, where x2 is greater than x1, which means that the second polymer has the number of segments in the second polymer is larger than the number of segments in the first polymer, that is the second polymer is longer than the first polymer. So, for such a case, if we let us say consider that polymer blend to be at a temperature where the delta Gm versus phi 2 graph looks something like this. It shows again two convex regions and a kind of concave region in the middle. So, if we have an asymmetric blend of this type, so as before for the case of polymer solution, we can here also start by drawing a common tangent to the two portions of this curve. So, the common tangent that is represented by a dashed line here, that basically will touch the curve at two different points, and the 2 points at which this common tangent touches the curve correspond to the binodal points, as we have already discussed when we are talking about the polymer solution case. So, polymer blends also a similar kind of construction can be used to identify the binodal points. Now that we have the binodal points, as before, the region marked by these arrows here, if you have the polymer composition in these regions, then the blend that forms will be a stable blend, or it will be a miscible blend. However, if the blend forms outside this region, so if the blend is formed in with a composition of the second polymer phi 2 in this region, which is again the miscibility gap for this case. So, in this region the blend will not be stable, in the sense that it can it will have a tendency to phase separate into two different phases. So, again we are not going to discuss in too much detail, because we have already had a discussion of the different aspects of such a diagram when we are talking polymer solution. But again in this case also we can identify 2 points which correspond to the condition of del square delta Gm del phi 2 square equal to 0. So, these 2 points where the second derivative of delta Gm becomes 0, these 2 points again will correspond to the spinodal points for the polymer blend. And if we have a blend that has a composition lying between the spinodal points, between these 2 points, then that blend will be unstable and will tend to spontaneously phase separate. And again the region between the binodal and the spinodal, so these two regions here, they correspond to the metastable state. If we consider an asymmetric blend which where the number of polymer segments is smaller in the second polymer than the first polymer. So, the first polymer has more number of segments, x1 is larger than x2, and if other things remain the same, then the phase or the Gibbs free energy diagram as a function of phi 2, that will appear to be just inverted form of what we saw in the previous case. So, in this case now the phase diagram or the free energy diagram actually will show a deeper minima on the left side and a shallower minimum at the right side, which is opposite to what we saw in the previous case where x2 was larger than x1. And again by using a common tangent construction we can identify the binodal points, and again one thing to remember is that the binodal points need not correspond to the points at which this curve actually shows minimum. So, the minimum might be somewhere here where the binodal point is somewhere here. Similarly, the minimum here might be somewhere here and binodal point is somewhere at a slightly different location. So, if we have asymmetric system, the binodal points will not necessarily correspond to the points of minimum on the free energy versus phi 2 diagram. So, next let us consider the case of a symmetric blend where x1 and x2 are equal, and let us represent both x1 and x2 as x. Since the blend is symmetric, we see that the delta Gm versus phi 2, that diagram is also symmetric, and if we again make a common tangent, do a common tangent construction, what we see is that the common tangent in this case is horizontal. The reason for that is since a blend is symmetric, the free energy diagram is also symmetric, and both the minima actually have the same depth. So, if we draw a common tangent which touches the curve at both these points, then that common tangent will be horizontal. So, for a symmetric blend the common tangent is horizontal, and mathematically if we consider the first derivative of the Gibbs free energy, which is an expression that we have derived previously in this lecture. So, instead of x2 and x1 we can replace both of them by just x. So, that is what we have done, and the expression for this first derivative which will correspond to the slope of this curve. So, that expression changes to or simplifies to this. And now we see that these two terms, since x1 and x2 are equal, these two terms actually will cancel each other. So, a simplified expression now becomes what shown here. So, now that the common tangent is horizontal, the binodal points that we have identified will coincide with the points at which the curve will display minima. So, that makes things easier mathematically in the sense that at the binodals, now since both the binodal points also correspond to the points of minima on this curve, so therefore, at the binodal points this one should be phi 2b double prime. So, at the both the binodal points, the slope of this delta GM versus phi 2 curve, which is the first derivative, that will be 0 at both the binodal points. Then since we already have an expression for this first derivative, we can set that equal to 0, and that will help us in determining the equation for the binodal curve. So, for a symmetric blend again, if we are setting this expression which is the first derivative of the Gibbs free energy to be 0, that will give us the equation for the binodal curve, because the condition that the first derivative is 0, that condition is satisfied at both the binodal points. So, if we again rearrange the terms, finally the chi parameter corresponding to the binodal point, that chi parameter expression one can derive to be this. In going from here to here, all we need to do is just rearrange the terms a bit. So, if we consider this term here, and if we are setting it equal to 0, then what we can say is that ln phi 2 by x minus ln 1 minus phi 2 by x, that will be equal to 2 phi 2 minus 1 times chi, where we have taken this term on the other hand side, and then we'll just take this on the other side as the denominator. So, that will give us an expression for chi b, and these two terms natural log terms can be combined because they have the same denominator. So, this x will come out as common in the denominator, and ln phi 2 minus ln 1 minus phi 2 will give us this ratio ln phi 2 over 1 minus phi 2. So, that is how we can obtain this expression for chi b, which is the Flory-Higgins interaction parameter at the corresponding to the binodal condition. And if we now again use the expression for chi as a plus b by t, then the temperature for the binodal curve, that expression can also be obtained. So, we just substitute this here, and that will give us this expression, and then finally we rearrange the terms, and the expression for the temperature is what we have obtained here. So, this equation or equivalent to this equation, these two equations basically are the equations for binodal curve for a symmetric polymer blend. So, if we plot T, the temperature or Tb as a function of phi 2 using this equation, the curve that we will get will be the binodal curve for our symmetric blend. So, now that we have identified the equations for binodal curve for the special case of a symmetric blend, let us now talk about the phase diagram, a typical phase diagram of a polymer blend. So, what we will see is that for a polymer blend also the phase diagram will contain features which are very similar to what we saw for polymer solution. The phase diagram that's shown here, this phase diagram is a generic case where we are considering a polymer blend that basically shows both upper critical solution temperature and a lower critical solution temperature. We can have polymer blends which show either one of these two, or some can show both these critical points. So, we are just discussing a general case where both these critical points are present on the same phase diagram. So, if you have a phase diagram shown here, which is just a plot of temperature versus phi 2, and we are just representing the binodal curves here, which mark the boundary between the single phase and the two phase region, or the single phase stable region and the two phase region, which can contain both metastable and unstable regions. So, if we look at the phase diagram, the single phase region is basically the region lying outside the two binodal curves. So, these two are the binodal curves here and here, and the region outside the binodal curve corresponds to the single phase region, and the regions being enveloped by the binodal curve, these correspond to the two phase regions. So, if we have a polymer blend at a certain composition and temperature which corresponds to this point, then it will basically phase separate into two different phases, one having these two compositions. Okay. The 2 points here, this point of maximum on this curve and this point on minimum on this curve, these 2 points are the critical points for this case, and because these 2 points correspond to the maximum or minimum on the binodal curve. So, the lower point is what is called the upper critical solution temperature. So, this is the maximum temperature up to which a two phase region can be seen, or phase separation can be seen. So, above this upper critical solution temperature, the polymer blend will become miscible throughout the composition range. But if we keep on increasing the temperature, for this particular case, we can again hit the two phase region at a much higher temperature, and that the minimum of this curve is corresponds to a temperature which is called the lower critical solution temperature, or LCST. So, this terminology was already introduced when we discussed polymer solution, and the same applies to polymer blends as well, UCST and LCST. So, this lower critical solution temperature again corresponds to a temperature below which we will have complete miscibility of the polymer blend throughout the composition range, and above this temperature the polymer blend actually can become immiscible or can phase separate over a certain composition range, which is basically the miscibility gap. So, here we have not we have only shown the binodals, but one should remember that just like for the case of polymer solution, for polymer blends also, if we try to draw the spinodal curves, the spinodal curve will lie inside the binodal curve and they will touch the binodal curve at the minimum point. So, the spinodal will also show minimum at the same point as the binodal, which is the critical point LCST, and for the lower curve also a spinodal can be drawn which will show a maximum at the same point as the maximum for the binodal, which is the UCST point, and the region. So, this is the spinodal curve. Similarly, this also we have drawn the spinodal curve here, and the region between the binodal and spinodal we have already discussed before is the metastable region, and the same applies here, and inside the spinodal we have the unstable region where spontaneous phase separation can occur in the presence of the tiniest of fluctuations. So, now let us consider the case a phase diagram which shows an LCST for a polymer blend, and let us see how the phase compositions can be determined. So, again we have a two phase region enveloped by the binodal curve here and the single phase region outside. So, the two phase region, one arm of the two phase region, let us call that the alpha phase, which will be rich in polymer 1. So, this corresponds to a lower volume fraction of polymer 2, phi 2 will have values less than 0.5 on this side. So, that will be rich in polymer 1, because polymer will have a higher volume fraction in that part of the phase diagram. And let us consider the other phase, let us call it the beta phase, and this phase will be rich in polymer 2, that is the volume fraction of polymer 2 will be higher in the beta phase than that of polymer 1. So, now that we have identified these two phases, let us see how, let us first consider the LCST point, which is the minimum of this curve, okay, and let us consider a point in this phase diagram which lies inside the two phase region. So, let us at some temperature T prime and some composition phi 2 naught, we are at a point on the phase diagram which lies inside a two phase region. So, if we are inside that two phase region, the phase separation will take place and will end up with two phases, one having composition given by phi 2 alpha and the other having composition given by phi 2 beta. So, they will correspond to the 2 points that are marked here. So, in the two phase region, if we let us say initially we are in the single phase region, and if we increase the temperature up to this point, then in the two phase region that homogeneous single phase of the polymer blend will split into two phases, and the two phases will have corresponding compositions. One will be rich in polymer 1, which is the alpha phase, the other will be rich in polymer 2, which is the beta phase. So, now let us see how we can determine the phase composition, which means how we can determine how much of which phase, alpha phase and beta phase will form. So, clearly the length of this line here is phi 2 naught minus phi 2 alpha, and the length of this line here is phi 2 beta minus phi 2 naught, that is obvious from the diagram. And let us represent the volume fraction of alpha phase by the symbol F alpha and the volume fraction of the beta phase by the symbol F beta. So, what can be shown is that the ratio of F alpha and F beta, that ratio is equal to the ratio of these two quantities here. So, if we look at the phase diagram, the numerator here is the length of this part, and the denominator here is the length of this part. So, using the phase diagram, one can actually identify the volume fractions of, let us say, the second polymer in the two phases that are formed, as well as the overall volume fraction of the entire two phase system. And using these volume fractions, the ratio of the fractions of the two phases that are present, F alpha and F beta, their ratio can be found. So, if we just rearrange the terms and note that this F alpha plus F beta, this sum is 1, then we will get this expression for relating phi 2 naught with phi 2 alpha and phi 2 beta. Here phi 2 naught is again the overall composition if we consider the two phase system together, and phi 2 alpha and phi 2 beta are the volume fractions of the second polymer in the alpha phase and the beta phase separately. F alpha and F beta, as we have discussed, is the volume fraction of the entire alpha phase and the entire beta phase. So, there since we have only two phases present, then some of their volume fractions will be 1, which is shown here. So, now if from this what one can see is that F beta can be written as 1 minus F alpha, and that we can substitute in place of this F beta here to get this expression. And if we rearrange the terms so that all the F alpha terms come on one side only, then we can obtain an expression for F alpha here, okay. And the expression for F alpha is this. Similarly, F beta is 1 minus F alpha. So, using that, the expression for F beta can also be obtained. So, what we see is that using the different compositions from the phase diagram, these three, we can not only determine the ratio of the phases that are formed, the two phases alpha and beta, but we can also find the individual volume fractions of the two phases that are formed. So, we can find the expression for F alpha, F as well as F beta. With that, we will like to conclude the discussion of thermodynamic behavior and phase diagrams of polymer blends. So, what we saw is that for polymer blends, much of the theory is similar to what we already discussed for polymer solution. The only difference is that in the case of polymer blends, both the components are polymers. So, both are long chain molecules, and hence the Flory-Huggins theory gets or the Flory-Huggins equation gets modified slightly by the inclusion of the number of segments of the other polymer as well. And due to this, what happens is that the entropy change of mixing, that for polymer blends is quite small and does not play a significant role in the phase behavior. Instead, the interaction term containing the Flory-Huggins polymer interaction parameter, that is the term which plays a dominant role in determining the thermodynamics of mixing or demixing of polymer blends. The other thing that is different between polymer solution and polymer blends is that polymer blends in many cases are actually immiscible. So, if we mix two polymers which are not very similar, then mostly they will end up being phase separated, that is they will not mix with each other. However, there are cases where polymers are almost completely miscible with each other as well. Also, if we have an immiscible polymer blend, then phase separation might lead to the formation of two different phases in a given material. So, although the two polymers are immiscible and strictly speaking have not formed a blend, but still such immiscible polymer blends are actually also have some applications. So, even upon mixing, if the polymer blends are not miscible, the material that forms still can show some favorable properties, and in fact there are many cases in which immiscible polymer blends are also used in applications. Further, if we have two polymer blends which are not very miscible with each other and which show phase separation, then their compatibility with each other can be increased by the process of what is called compatibilization, where a third component may be added, which is the compatibilizer to this polymer blend. And what this third component can do is go and sit at the interface and basically improve the interfacial interaction between the two phases of this immiscible polymer blend. So, here the compatibilizer that we add, one example of compatibilizer material can be a copolymer, where one part of the copolymer basically is miscible in one of the polymers of the polymer blend, whereas the other part is miscible in the other polymer of the polymer blend. So, if we have such a case, then what will happen is that at equilibrium the this block copolymer, so we are talking block copolymer here. So, this block copolymer, one block which is which prefers the one of the polymers of the blend will try to reside in that phase, whereas the other block will reside in the other polymer phase of the blend, and that will improve the interfacial interaction. So, even for immiscible polymer blends, the compatibility can be improved by the incorporation of compatibilizers. With that, we will conclude the discussion of polymer blends, and we will just briefly discuss the thermodynamic behavior and phase behavior of block copolymers next. So, a block copolymer, if we have a block copolymer, let us say as shown in this diagram here, which consists of two blocks. So, if we have a diblock copolymer, where one block is let us say is called block A and the other block is called block B, then if the blocks A and B, or the repeat units in the blocks A and B, if they are not chemically compatible with each other, which means that if they are not interacting favorably with each other, then they will such a copolymer will also have a tendency to phase separate. However, unlike a blend, in the case of block copolymer, the blocks of the copolymer are actually linked by the presence of covalent bonds. So, if we have a blend where the two polymers are not liking each other, then the blend can basically phase separate easily into two different phases at the macroscopic level. However, in the case of block copolymer, since the two blocks which let us say are not chemically compatible. These two blocks do not like each other, but since they are covalently linked at a point, they are not free to just phase separate at the macroscopic level. So, what instead happens in the case of such block copolymers is that the macroscopic phase separation does not occur because of the constraint of covalent bonding between the blocks. However, the microphase separation can take place. So, at a microscopic scale or even at the nanometer length scale, the phase separation is actually observed for block copolymers. So, now when phase separation occurs at the microscopic scale, then spatial scale or the length scale over which structures are formed in such phase separated material, that length scale is comparable to the size of the polymer chains that are present in the system. So, the when microphase separation takes place, the phase separated ordered structures can form, and we will look at some of the ordered structures very soon. So, these phase separated structures that are formed, their length scale will be determined by the lengths of the polymer chains that constitute the system. Whereas the morphologies, so apart from the length scale of these ordered structures that are formed, the morphology of the ordered structure, so whether we get kind of a lamellar morphology or a cylindrical morphology or some other kind of morphology, what kind of morphology will form, that is governed by the composition of the constituent repeat unit. So, what we mean by this is that the relative amounts of A and B present inside the block copolymer, that will basically dictate what kind of morphology will be observed if the block copolymer phase separates at the microscopic level. When we talk about phase separation in block copolymers, there are two factors which are governing this phase separation behavior or the microscopic phase separation behavior. So, first factor is the fact that the interaction between the two blocks is not favorable, the two blocks are not chemically compatible. So, the interfacial area of contact between the microphases that are formed containing the two different blocks, that interfacial area should be minimum. Okay. So, the system attempts to minimize this interfacial area so as to reduce the number of unfavorable contact interactions. However, since the polymer is phase separating, where one block forms part of one phase and the other block forms part of another phase at the nanoscale level, this kind of phase separation can lead to stretching of the polymer chain. So, this chain stretching actually is entropically unfavorable, because stretching the chain will reduce the entropy change associated with the process, and which is not favorable for mixing. So, there are these two competing or opposite effects, where the interaction basically is unfavorable. So, that will try to minimize the interfacial contact area, but in doing so, the stretching of the polymer chain should not be such that the system loses too much entropy. So, these are the two competing factors which are important in the phase separation behavior of block copolymers. And from the point of view of the different parameters, system parameters that are important for the phase separation behavior and the structures that are formed upon phase separation. So, there are three parameters that are important from that perspective. One is the amount of let us say amount of a block of one type that is present in the system. So, if we have blocks of two type A and B, and let us say if Fa represents the volume fraction of the total blocks of type A, then and that composition which is represented by Fa, that will be one factor which will govern the phase behavior and the order structures that form upon phase separation. Another important parameter is again the Flory-Huggins interaction parameter, and this Flory-Huggins interaction parameter chi is the interaction parameter between the A and B blocks of the system. And finally, the third parameter that is important is the overall degree of polymerization of the system. So, how long the polymer chains are. So, these three parameters, the composition which is characterized by Fa, the volume fraction of instead of component A, we should maybe using the terminology block A will be more appropriate here. So, the copolymer composition will be an important factor, the overall degree of polymerization x and the fluorescence interaction parameter chi, these are the important parameters. Now, the phase separation that microphase separation that takes place in block copolymers, that is typically referred to as order disorder kind of transition, where a homogeneous molten diblock copolymer can phase separate into heterogeneous microphases of different morphologies. So, this order disorder transition that we have, this is seen to occur at a critical value of this product x times chi. So, this product x times chi, if the critical value of at a critical value of around 10.5, this order disorder transition from molten homogeneous copolymer phase to a phase separated microphase separated heterogeneous phase, that is observed for symmetric diblock copolymer, and this is actually predicted by theory which involves a mean field approximation. So, if the value goes above this, then microphase separation is expected to take place, and if the value of this product is less than this critical value, then we'll have an homogeneous molten state of the polymer solution or the block copolymer. So, when we say symmetric diblock copolymer, what we mean is that the diblock copolymer has equal numbers of or equal sizes of the A and B block. So, essentially Fa is equal to 0.5 in this case, that is what the term symmetric here means. Finally, if we try to look at the phase behavior of block copolymers from using some kind of a phase diagram, then if we consider the fluorescence interaction parameter and its dependence on temperature to be given by this expression, which we have been using for other systems as well, and for block copolymers also such a dependence is found to be the most common kind of dependence. For such a system, for such a dependence of chi on temperature, for block copolymers mostly this quantity or parameter B is greater than 0. So, T increase for these systems, an increase in T actually leads to a decrease in chi. Okay. So, a decreasing chi will mean an increasing temperature, and an increasing chi means a decreasing temperature for the case that we will discuss. And for the diagram that we will discuss next, the condition under which that diagram has been drawn is that the system is conformationally symmetric. So, this actually should not be confused with the symmetric block copolymer that we discussed in the previous slide. Conformationally symmetric means that the size of let us say given segment. So, let us say this block B that we have here and the block A here. So, let us say the size of the segments that constitute this block B and the size of segments that constitute block A. So, the A and B blocks segment sizes are equal, that is what this condition implies. Okay. It has nothing, does not imply that the amount of A and B block is the same. A typical phase diagram or something that is representative of a phase diagram for a block copolymer system is what shown here, and it has been adapted from this textbook by Young and Lavelle. So, here on the x axis we are plotting Fa, which is the composition of or the amount volume fraction of the A block in the system, and on the y axis you see we are plotting this product chi times x. Okay. So, as we discussed in the previous slide, the critical value of this chi times x is around 10.5 for symmetric block copolymer. So, symmetric block copolymer will correspond to this 0.5 composition, where Fa is equal to Fb and both are 0.5. So, we see that at this composition the value of this chi times x is actually close to 10.5 in this plot as well, and we can identify different regions in this phase diagram. So, the region here region enclosed by the black curve here. So, that region basically corresponds to a microphase separated system where lamellar kind of morphology is observed. Similarly, the region on this phase diagram lying between the black curve and the red curve on both sides, this corresponds to what is called a bicontinuous gyroid kind of morphology in the phase separated microphase separated block copolymer. And if we go further away from the symmetric condition, which is Fa equal to 0.5, if you go further on either side, then other morphologies can be seen. So, next at higher Fa values as well as on the other side at lower Fa values also, this cylindrical kind of morphology can also be observed. And finally, between this blue and the green curve here on both sides, the microphase separated copolymer will can show sphere like morphology. So, and the region that is outside the phase envelope that we have here, the region here, this is this represents the disordered state. So, in all the points outside the phase envelope that we have drawn, the system will be in a disordered state, which means that it will basically be a homogeneous single phase system at the macroscopic as well as the microscopic level. Whereas in the microscopic phase separated domains, although macroscopically the system any phase separation might not be visible, but at the microscopic level, which is at the scale of 1 to 100 nanometers, let us say, distinct ordered structures representing phase separation will be can be observed. And typically experimental techniques such as transmission electron microscopy or small angle X-ray scattering, these techniques can reveal these microphase separated morphological features in such block copolymers. So, so all the different morphological states that we have identified here, if we try to visualize them, then this diagram here, which has been taken from this article by Botez and Darling from Materials Today, this article this figure very nicely shows what the different kind of morphologies are which can be expected as we change this composition of the A block, which is changed by increasing this Fa. So, if Fa is small, which is which let us say at small Fa, let us say if we are in this region at small values of Fa, then the B the what we discussed earlier is that spheres will sphere like morphology will form. So, what will happen is spherical domains of A will form in a continuous phase formed by B. So, the blue region here is B and the spherical domains that we see, that is A, and as the value of Fa is increased, we will move from sphere to the cylindrical morphology, where the again A will form this hexagonal closed pack cylindrical phase and B will still remain as the continuous phase as shown by the blue part here. And at if the composition of A is further increased, a gyroid kind of bicontinuous gyroid kind of morphology as shown here will be seen, and upon further increase lamellar morphology will be seen, where the two blocks A and B will arrange themselves in flat layer by layer kind of morphology. Okay. So, here the red layer represents again A and the blue layer represents B. And if we keep increasing the composition of A further, then again we will move back into the gyroid kind of morphology, but the only difference is that now since the amount of the block A is higher now, so that A block that will form the continuous phase and the B will form the discrete phase. And similarly at again higher Fa will get go into the cylindrical morphology, but now the cylinders will be of B, A will be the continuous phase. And finally, at higher morphologies we will get A as a continuous phase again and spherical morphology of B. So, we see that for the case of block copolymers, many interesting order structures can be observed at the microscopic level. So, the phase behavior of block copolymers is actually quite interesting and leads to a very nice and a variety of morphological structures of whose length scale typically is of the range of a few nanometers to few tens of nanometers. So, again the specific type of morphology that will form depends on the composition. So, how much of the block copolymer is actually block of type A or how much is block of type B, that relative composition basically dictates the type of morphology formed. And as we discussed earlier, the size of the polymer chains that are present, that will dictate the length scales of the these order structures like sphere or cylinder or lamella that are formed. So, what we can conclude is that for block copolymers, macro phase separation as seen in the case of blends does not occur because they are covalently bound, the blocks are covalently linked to each other. But if the blocks constituent elements of the blocks do not like each other, they are not chemically compatible, then at the microscopic level or at the order of a few nanometers, the polymer will actually phase separate. So, a microscopic phase separation will take place and interesting ordered morphologies can be observed. So, with that we conclude our discussion of thermodynamics of polymer solutions as well as that of blends and block copolymers. And to summarize, what we have discussed is a mathematical description of the thermodynamic behavior of polymer solutions as well as blends using the Flory-Higgins equation. We have also discussed the solubility parameter approach which can give a good estimate for the miscibility of a polymer in a solution, and this solubility parameter approach can also be applied to blends in a similar way. So, if the polymers constituting a blend have similar solubility parameters, they will be more miscible. So, apart from that, we have discussed the phase separation behavior, the regions of stability, instability and metastability in detail. We have also talked about how to identify the binodal points, the spinodal points, as well as constructing the phase diagrams and identifying the critical points on these phase diagrams. And for the case of copolymers, we have also discussed that different kinds of interesting microscopic morphologies can be observed upon phase separation at the microscopic level. So, that is a summary of what we have discussed under thermodynamics of polymer solutions and blends and copolymers. In the next lecture, what we will do is start discussion on the different techniques that can be used to measure the molar mass of polymers. So, polymer molar mass, as we will see, is a very important characteristic of any polymer sample, and actually a lot of macroscopic properties depend on the polymer molar mass. So, good knowledge of the polymer molar mass is important, and in the next few lectures we will discuss different techniques that can be used to measure the different types of average polymer molar masses that we have introduced in the very first lecture of this course. Thank you.